Hello and welcome to another lecture on three-dimensional geometry. Today we shall be discussing about the Cartesian and vector equation of a line. Later we are going to discuss what are coplanar and skew lines, and finally we shall conclude this lecture based on three-dimensional geometry by discussing some numerical problems that would be based on the topics that we are going to discuss in the coming segments of this lecture. Now we are going to discuss and evaluate the vector equation of a given line. But before we know that, in space a straight line is uniquely determined if it passes through a given point and has a given direction, or if it passes through two given points. We shall now obtain the vector equation of a line. Here we are going to consider a straight line that is passing through a given point and is parallel to the given vector. Here, let the line passes through a point A with position vector A, and let it be a parallel to a vector B. And now let P with position vector R be any point, then P lies on the line with the condition that vector AP is parallel to vector B. That is, if and only if vector AP is equal to lambda B, where lambda represents a scalar or a real number. That is, if vector OP minus vector OA is equal to the scalar product of lambda and vector B, or we can say that the position vector of P, which is R vector, minus position vector of A, that is A vector, is equal to lambda into vector B. This can be further rewritten as the positional vector of P equal to vector A plus lambda vector B, which is the required vector equation of the line. Next we are going to consider the Cartesian form of a given line. For that, let us consider a point A with coordinates x1, y1, z1, and A, B, C be the direction numbers of the line, and P be a point such that it has the coordinates as x, y, and z, and the vector R is given as x I plus y j plus z k, and vector A is equal to x1 I plus y1 j plus z1 k, and vector B is equal to A I plus B j plus C k, where I, j, and k represent the unit vectors. These values are going to be substituted in the equation that we have found for the vector equation in this lecture, which was vector R equal to vector A plus lambda vector B. Thus, substituting these values, we have x I plus y j plus z k is equal to x1 plus a lambda unit vector I plus y1 plus b lambda unit vector j plus z1 minus c lambda into unit vector k. Now on equating the coefficients of the base vectors I, j and k, we have x equal to x1 plus a lambda, y equal to y1 plus b lambda, and z equal to z1 plus c lambda. These are known as the parametric form of line, and any point on the line is p x1 plus a lambda 1, x2 plus b lambda, x3 plus c lambda. On eliminating the term lambda from equation 2, we have the equation as x minus x1 divided by a is equal to y minus y1 divided by b, which is equal to z minus z1 divided by c. This is the required Cartesian form of a line and is also known as the symmetrical form of a line. Next we are going to discuss the coplanar and skew lines. The lines lie in the same plane are known as the coplanar lines. In fact, two parallel lines or two intersecting lines always lie in a plane. Thus, two lines are coplanar if and only if they are either parallel or intersecting. Next, we are going to consider the skew lines. Two straight lines which are neither parallel nor intersecting are called as skew lines. Two skew lines are always non-coplanar. Next, we are going to discuss the condition of coplanarity of two given lines. For that, let us consider two lines L1 and L2, where line L1 is given as x1 minus x2 divided by a1 equal to y minus y1 divided by b1 equal to z minus z1 divided by c1, and L2 is equal to x minus x2 divided by a2 equal to y minus y2 divided by b2 equal to z minus z2 divided by c2. The given lines are coplanar if and only if the determinant of whose first row is x2 minus x1, y2 minus y1, z2 minus z1. The second row is a1, b1, c1. Third row is given as a2, b2, c2. Now if the value of this determinant is equal to 0, then the given lines are coplanar. Finally, we are going to deal up with a problem which states that show that the lines given as first line is x minus 1 divided by 2 equal to y minus 3 divided by 4 equal to z divided by minus 1, and second line is x minus 4 divided by 3 equal to y minus 1 divided by minus 2 equal to z minus 1 divided by 1 are coplanar. Now, as already discussed, that the lines with the equation x minus x1 divided by a1 equal to y minus y1 divided by b1 equal to z minus z1 divided by c1, and the second line is x minus x1 divided by a2 equal to y minus y2 divided by v2 equal to z minus z2 divided by c2 are coplanar if and only if the value of the determinant whose first row consists of elements x2 minus x1, y2 minus y1, z2 minus z1, second row consists of elements a1, a2, a3, and third row consists of b1, b2, b3. Now for these two lines to be coplanar, the value of this determinant must be equal to 0. Therefore, the given lines are coplanar if the value of the determinant whose first row is 4 minus 1, 1 minus 3, 1 minus 0. Second row has elements as 2, 4, minus 1. Third row is equal to 3 minus 2, 1. For coplanarity, this determinant must be equal to 0. That is, the value of this determinant with the row 1 as 3 minus 2, 1, second row 2, 4, minus 1, and third row 3 minus 2, 1 must be equal to 0. Thus, to prove this, we need to evaluate the value of this determinant, which is equal to 3 into 4 minus 2 plus 2 into 2 plus 3 plus 1 into minus 4 minus 12. Now evaluating this, we have the value of this determinant equal to 0. Thus, two given lines are coplanar and it has been proved. With this, we conclude this lecture on three-dimensional geometry, which was based on the lines and their equations.